So in the instrumentation, we started with the X-rays, right? The X-ray tube configuration, and then just after the X-rays come out of the X-ray tube, which is going to be a spectra of energy, we wanted to do two things. One is do the filtration so that only the energies that have maximum probability to give you signal, right? You don't want too high a signal, you don't want too low a signal, and so there is idea of filtration. And we just concluded restriction. What is restriction? It is just to cover the field of view. You don't want to send the X-rays to regions that are not going to be part of the imaging, so as to avoid dosing the patient. Okay. So after that, so we had the source part, right? Just outside the source we talked about filtration, restriction. Now what about the instrumentation? Are we going to instrument the patient, or should we go to the detector side? What is your guess? Well, really speaking, it's how you, when we talk about instrumentation, you think about, oh, there is the physics, there is a concepts, right? The physical phenomena and other things, and then instrumentation is trying to achieve. So it's part of engineering, right? So you want to achieve, make use of this knowledge, make use of this understanding to realize something. So in some sense, even though the interaction of the X-rays that are coming with the tissues, right, which the object, that itself is governed by physics, but our job here as engineers is to maximize the signal, minimize the noise, right? I mean that, so that you can make a measurement that can be used reliably as an estimate of your underlying unknown. So in some sense, we need to also talk about, in the instrumentation only, about what happens with the humans. Can we manipulate the material right, to get good signal to noise ratio or contrast to noise ratio? Okay, so we'll probably the name we did talk about, hint of contrast agents earlier, but we will go through the motions here. Okay, so what do we mean by compensation filters, right? So this is essentially to think about, I cannot really engineer the human being. I mean, right? I'm going to go in my native state, get an image, but what I can do is I can make this instrumentation to some extent customize it, right? So that for me the signal to noise ratio is good. For me, when I say, depending on the object of interest. So that means if I go for a chest X-ray, or if I go for a head and neck, or I go for an arm, or I go for a leg, right, or my foot, each organ is different. So depending on which organ you are doing, can we compensate for some losses that we know the physics has told us. So when we built our material, we used a thickness, right, of a slab as delta X. So we just used the thickness. So the thickness was same throughout the height. In our context, narrow beam. So the thickness across the slab was same with respect to in the region where your detector is seeing. That's what we did. But in reality, that need not be the case, and therefore based on that we developed the signal and photoelectric effect, Compton scattering, and we said the signal attenuation is dependent on the material property mu and length of the material. So mu delta x, e power minus mu delta x, right? So now the question is, okay, that means what we developed, the material that we interrogated had a uniform slab thickness across. So all our equations were right for that. We didn't really make it a point that the length changes, across. We didn't encounter that. But really, if I go stand, right, when you have an object which is a 3D object like a human body, the thickness is not same throughout. The thickness is changing. What is our objective? Our objective is to find out the mu that is differentially distributed, right? But what is the attenuation law tell you? I send some n photons in, some reduced photons come out and hit the detector. So this loss is proportional, and we said we modeled it as a exponential loss, right, e power minus mu delta x, and therefore we can infer about the material mu through which, so the loss is proportional to the material, but we said material into delta x. So the loss, so you could have a highly attenuating material, but delta x could be small, or you can have a weak attenuating material, the mu could be low, but your delta x could be large. In either case you will get the same, see that is the problem with the projection, right. So you will either case get the same loss. So material has not changed, it is only the length that has changed. So therefore the concept of compensation filter is, if I know a priori, right, if there is a difference in the material length delta x, because mu I do not know, if I know mu, job done, I do not know the delta x, but if I can know the delta x, make a guess on the delta x, which is not difficult, right. I mean I have a thickness, I know that probably I am fat at the center, and as I go towards the side I am less thinner, right, the depth is reducing. So you can have a rough idea on how it is. Or if I go for my foot, right, I cannot show the foot here, but you look at your foot, I will have a sketch next. But the idea is, you can have scenarios, you can have parts that you are going to image, where you know upfront that the depth through which the X-ray is going to go is going to be different. So maybe instead of sending the same number of photons, and the differential instead of differential attenuation, it's the path length that is different, that is giving you the lower signal, then your differential attenuation is not captured. So what I can do is, maybe if that is the scenario, then my objective is to make the path length same, right, but then I cannot change the path length. So what I will do is, instead I can send the photons, so that irrespective of the length, that is normalized. So I can send more photons when it does go through some delta x. I can send, right, I can send the same photons here, but then when it goes in, I could have some material that is shaped to absorb the photon. So when it hits the material, the same number of photon goes through the thickness. So depending on the thickness, I can have additional compensation filter, right, that is going to allow proportionately same number of photons go through the thickness per length. You can normalize it per length. Okay. So where are the scenarios? So this is straightforward. So if I show you some examples, you will get the point. So here, for example, the photons come here, right. If I didn't have this wedge shaped filter, what would happen? Here the X-ray is going through lot more path length of the tissue. Here it is going through very little. So if you can relate this to your delta x that we derived, so delta x is more here, delta x is less here. If this material is same, even if this material is same, mu is same, you can clearly see the loss is more on this side, because the path length is more than this side. So if I don't have any ways to tell that the compensate for this difference in path length, your plain interpretation would be, there is more attenuation this side, less attenuation this side. So the material is more attenuating here than this side, which is not true. The material is same. It is just that the path length is more on this side, path length is less on this side, right? The path length. So the length of this line that is passing through the material, right? That is what. Clear? So that means in this case, we a priori know that there is a path length difference because of the shape of the object, and therefore you could come up with a compensation filter where you are essentially increasing this right, this length and this length put together, this length and this length put together, more or less the path length is same. Therefore whatever loss you are getting, right, is going to be proportional only to your differential material property, subtle material property, correct. So this is why it is compensation filter, because you are compensating for this change in path length through the medium. So you are trying to compensate for that. So there are two variables in your attenuation. One is mu, the other is delta x. By using this compensation filter, you are trying to make sure that delta x variability is reduced. So whatever differential signal that you get is only because of the mu that is along the path and not the length of the path itself, right. So here is one typical example. Here, like I said, for when you go for chest, you know, the front to back distance, right, the depth at the center of your body is more compared to your sides, right. So that is your delta x in your slice thickness that we talked about when we slab thickness, right. So you could have a wedge that is having through filters, right. You have a less length here, more length here, therefore the path length more or less is similar. Likewise here around the neck. So you could really think about this. So very application specific. We are not engineering the patient, but then it's still to do with the patient. So depending on the patient's, your target, right, your object or your human. So based on that, so this is part of instrumentation in that sense, right. So you had the source side, this has to do with the object side, right. So that is with respect to your compensation filter. So next is your contrast agents. What did we talk about contrast agents? In the brief intro that I said when we talked about contrast, right. So here again we are not engineering. So why is this part of instrumentation? So there is a inherent contrast, the 3D distribution, right, and the instrumentation of generating the X-ray and detecting it is all on the outside. But why is this part of covered part of instrumentation? Oh, because you are talking about capturing the inherent contrast, right, of the f of xy, the contrast in the f of xy that needs to be captured. So here is a way, it's not natural, but there is a way where we can increase the manipulate the inherent contrast. That's why this is part of instrumentation. So what do we mean by contrast agent? Oh, we talked about this before. So some agent, so some trace quantity that you can send it into your body, and that has a mu, specific mu, right. If it turns out that that mu is different from rest of the body parts, like your soft tissue, fat, bone, if that is different from your body part, then wherever contrast agent is in the line of the X-rays that are going through, you will be able to detect it or contrast it out. So the idea of introducing contrast agents is to increase the contrast of those locations where the agent is sitting, okay. So we talked about this curve before, but there is a subtle addition in this. So this is your previous curve where we talked about photon energy and attenuation coefficient. Last time when we had this, we had only bone, muscle and fat, only the three curves were like this, and that time we talked about, oh, you have to choose an energy where you can have very good separation between the different tissue material. However, we said if it is too low energy, the attenuation is high, like the differential attenuation is also there, but the attenuation is high that it won't come out. So that is why we are going, and if it is too large, right, the photon energy is too large, then the inherent contrast between the various material of bone, here for example bone, muscle and fat, is reduced, right. So there is a sweet spot in between. That's why our X-ray energy, remember the waveform or the spectrum that we plotted outside the X-ray, all the filtering that we have done. So we have carefully come up with the X-ray energy that can maximize your interaction. So now what is added here is you suddenly see this sharp edge, right, this sharp edge that you see. What is this sharp edge? It is called as a K edge. Why is it K edge? Any guess? Of course, this is not your muscle or fat or anything. Here is one material, right? You have a plot for your barium, the other is for iodine compound. So there is a barium compound, iodine compound, and this is its characteristic curve of the energy and linear attenuation. Why is it called K edge? Any guess? Well, remember the interactions that we talked about. Photoelectric, when we talked about photoelectric, when we talked about the probability of photoelectric interactions, right? We talked about this energy levels. At that time we mentioned that if it turns out that the energy that is coming in is close to K shell binding energy of a material, there is a sudden increase in probability of your photoelectric effect. Go look back at the probability of interactions that we talked about. That time we mentioned that it is noticed that suddenly when the X-ray energy is close to a material's K shell binding energy, then clearly there is a maximization of the effect. Okay, and it turns out that if you so choose your compound so that there is a material property, the K shell energy, binding energy is close to your diagnostic X-ray energy. So here are examples of a iodine compound and a barium where the K shell binding energy falls within the X-ray energy of interest. Suddenly you see the attenuation coefficient just at K increases. So this is your K edge. Because of that reason, your K shell binding energy is so positioned within your diagnostic X-ray range that you are operating, that there is a rapid or a edge, right, increase in the attenuation coefficient. Okay, and clearly you can see what does this help. Oh, this helps. Suddenly you have your attenuation coefficient of the material that you introduce is way different to the other soft material that you are having here, bone or a muscle or a fat. So clearly, if the inherent contrast between the material that you have engineered which has a K edge, which pushes the attenuation coefficient high, and the native material, right, native soft tissue, the difference between their attenuation coefficient is increased. In other words, you can increase the contrast in the image, right, because the spatially wherever this material is there, the attenuation going to be way higher compared to where the soft tissue is. So you can easily tease out where this compound is in the path. Okay, so when the X-ray energy exceeds the K edge, right, that's why it is K edge, binding energy of the K shell, the mu is your attenuation coefficient is much higher, providing a high contrast. So we can maximize the contrast, inherent contrast. So in some sense this is not instrumentation, but this is part of instrumentation, because you have to choose your energy levels and you have to choose the compound carefully, right, so that you maximize the inherent contrast. Okay, so what are the typical compounds? Say for example iodine. You might know from basic knowledge that iodine, your thyroid is a natural center for iodine, right? You would have seen maybe 6th standard, 7th standard textbooks, goiter and iodine, salt, all these things you would have been familiar. So iodine has a activity in the thyroid. So naturally, if you want to do a thyroid imaging, right, you send X-rays because iodine is there and you saw the K edge. So it's a natural, the contrast of thyroid will be very good because of this region, because iodine is already there. Okay, so thyroid imaging, it gets natural benefit. You don't have to inject the contrast from outside. Okay, so what about other places? Oh, other places maybe I can come up with. So this is a natural material which is biologically safe, right? Iodine. So I could create some compounds of iodine. So it can be synthesized outside and into a safe soluble compounds and then inject it, right? So essentially I want to give it into the body, send it into the body. So if I send it into the body, what happens? Oh, it's going to go through the circulatory system. When it goes through the circulatory system, what happens? oh, wherever this iodine is going to go, when the X-ray is crossing path, it is going to attenuate that. So, in some sense, when it goes to the circulatory system, you can then capture, send the X-rays through and say, okay, this is where the iodine is going, right. So, you can track, even like in fluoroscopy, that's what we do, right. It basically tracks in real time, you see where all this iodine compound is going in the circulatory system. Of course, you can also see where it goes and settles, right. It has to go through your, for example, circulatory system, and it goes, remember, it will go through kidney. So, you could also do kidney imaging, then from kidney, bladder, right, it's trying to be sent out, you can do bladder imaging. So, all there where you can have a very good contrast. So, there are huge number of applications where your contrast agent using iodine is very useful and very standard. So, for example, blood vessels, right, it's going through the circulatory system, wherever it is going, you can start to see the, so if you have a block in the vessel, right, so blood will have only small region where it is going. So, the vessel cross section will be reduced because of this plaque or whatever obstruction. So, you can clearly see when you send the dye, when you send the iodine compound, you can actually infer that the vessel is reduced, correct. Heart chamber, so wherever the blood goes, tumors, where tumors, because again, if there is a tumor, that means there is a blood supply is there, it's growing aggressively. So, you can look at where the blood vessel is going. So, based on that, you can also see the tumor. So, if you have unusual activity, unusual vasculature, you can start to see tumors, infections, kidneys, bladder, right, because circulatory system, then it goes to the kidney and then through the bladder and sent out. So, wherever, if you give this into the system, it has to go through the circulatory system, wherever it is going, you can look at it, okay. So, this is one very common contrast agent. The other, you can think about a barium that you saw, right, there was another plot with barium. So, this is again a solution, it is administered as a milkshake, chalky milkshake. Essentially what it is why it is chalky milkshake is, if you shake it, right, if you put chalk, it will look like a milkshake. Never, I mean, it's not going to be tasty, okay, unlike your regular milkshake where you might enjoy drinking it. This is going to be not so enjoyable, right, not so tasty, but it serves an important purpose. Why? Because if you drink, see, there are ways to send it into the body. So, if I want to, for example, image the GI tract, right, is there a problem in GI tract, or if I want to see after GI tract, stomach and then bowel, right, it is going through. So, what are the things I need? Oh, I need the milkshake wherever it is going, right, that time if I send my X-rays, it is going to interact with the X-rays and attenuate. So, wherever it is going, along that path, right, when you projection is what we are doing, along that path we will be able to do get higher contrast of your native material against what you are sending. So, if there is a obstruction, right, if there is an obstruction or if there is a scar, if there is whatever structurally whatever is changing, you will be able to look at it. Of course, one of the ideas of using this is, it is, even though it does not taste good, it does not take part in the activity. So, it is kind of a passive in that sense, it just goes through, it does not interact, react, it just goes through the path and comes out. That way, functionally it does not alter anything, it does not interact with so that is important aspect as well. You do not want to drink something and then it starts to digest and create trouble, right. So, this one essentially goes through, retains the path and comes out, and therefore, this is very useful in imaging the GI tract if there is any obstruction, growth, tumor, lesion, whatever, okay. So, these are some compounds that you can prepare and routinely used. Then we have something that is not really engineered from outside, right. I mean, you can use air also as a contrast agent. Can you now guess what that does mean? I mean, so what we talked about barium and iodine, it has higher mu, right. So that means there is going to be lot more attenuation when X-ray energy is interacting with mu. So compared to the soft tissue, the attenuation is going to be more. Our contrast is always difference between two guys, right? F max minus F min, go right. So our F background, F target minus F background is the difference between the target and the background. So what have we done? I have by taking barium or iodine, if my target is where I want to see, the target mu is reduced. My background might be same, but my target is reduced. So the difference is increased. So the contrast is increased. But air, what does air do? Oh, air also attenuates, but probably it doesn't attenuate so much, right? So probably the air attenuation is less compared to your soft tissue. In other words, it in some sense this is having an opposite trend to the iodine and barium that we saw just now. Okay, that means if air is in the path, right, then compared to soft tissue, air will have less attenuation. Okay, so now the question is, okay, air is having less attenuation, how do we engineer that in the body? Think about, one is circulatory system, how else can we get something into the body? Breathing, right? Remember our respiratory physiology that you would have covered in your anatomy, physiology kind of courses. You can have air, you can inhale air, exhale air, right? So air is going inside the body. So if I want to do chest X-ray, I have lungs sitting there where a appreciable volume is there in the path where the X-ray is going to go. So by inhaling, I can have more air, so I can have path length change with more air or less air. So in some sense, this is creating a contrast in a opposite sense, right? So now the attenuation is less here compared to the surrounding tissue. So the difference between your soft tissue and your air is going to be increased. That means this will allow us to actually image with better contrast the lung tissue. In some sense, this is also a contrast agent, but it is doing the opposite effect, right, of having less attenuation. So does not absorb X-ray, opposite type of contrast. So you can inflate the lungs, right, to get in air, that provides a good contrast for your lung tissue. Clear? So we were talked about increasing. So if you talk about the target, I can either, for the same background, I can reduce the target intensities, thereby the contrast is increasing, or I can do the opposite, right? I can do the opposite for a given background, the target is increased, or I can have this same, I can reduce this for a, right, for air attenuation is less, it is going down. So for given soft tissue, if air is in the path, air is going to go down, and therefore a good contrast is going to be obtained. In case of the other one, barium and iodine, the soft tissue is here, barium or iodine is going to go up, right. So we can separate the difference. So contrast is increased. Is there any other way to exploit? Oh, I could actually do both. I could do both, right. I could give, for example, if I want to do bladder or bowel or something like that, I can have air also, right. The air is there, there could be air, and you could have this barium. So if I take barium, attenuation is increased. If I have air in bowel, attenuation is reduced wherever the air is. So in that image, you have very good dynamic range, very good contrast, because you have both the effects. Okay. So in some sense, you might, air is trivial, but then it could be used to your advantage if you know which target you are doing and what is your application. Okay. So much for compensation and contrast agents, right. So now comes the, you have source, body, right? You have a compensation and contrast agents had to do with the engineering the or maximizing the signal part, involving some tweaking with the object in place, and then you have your detector side. So whatever goes in interacts with the body, comes out. So now it is time for us to do two things. One is the instrumentation, so that we can catch whatever is coming back, not only catch whatever is coming through the body, right? It has to have good signal to noise ratio or contrast to noise ratio, right? So what is our signal? It is coming through the body, having interaction, and then coming out, number of photons, X-ray photon. What is our noise or detrimental interaction? The Compton scattering, what is going in, but then because of the interaction it is scattered out, right? So when I stand at the detector behind, I have to catch the signal, I have to minimize the photons that are coming due to Compton scattering. Okay. So two things we need to understand in the instrumentation. One is, how do I accomplish this of maximizing my signal, minimizing the Compton scattering. Next is, after I know that is the signal that has come through the path, how do I convert it into a image, right? What are the sub modules, the instrumentation that is used to convert this into a image. Okay. So first is, what is the ideal path? What do I mean by ideal path? Oh, we have the X-ray source, and we talked about X-ray source as a cone, right? It is sending out. So source itself is small and it is traveling the distance and it is diverging. No matter what, even if it diverges, it is always traveling along a line. So if I have a detector, so if it is traveling at an angle, right, simple case, if it is traveling straight, I expect it to come out straight. That is going to be my signal. Along the path line there has been interaction. So it is hitting, if it is diverging, it is going to hit at an angle and it has to come at the same angle. So it will take the straight line path. So ideally you want only the straight line path, in which sense I can say, if I have my detector, it is hitting, right, I can say that it actually came through the line that is ahead of it, in front of it. The interaction took place along the line in front of the detector. So the line connecting the detector point to the source point. So the material was along the line. That is our ideal scenario, right? That is ideal signal. So we expect the path to be a line. Clear? So naturally you have to do two things. One is, if that is the case, I want to ensure that whatever came through scattering, right, I can say that it is not my signal. So if it does not come along the line connecting the detector to the source, that is something that I do not want. That is something that I want to avoid, right. So essentially your grids, air gaps or scanning slits, we will quickly run through each of them. Their objective is to enable this, enable minimizing the signal that is entering from scattering, Compton scattering, and maximizing the photons that are entering through the straight line path, right. So in some sense you are trying to get very good signal to noise ratio, right. In order to get that, you have these instruments to first increase the chance of your signal and minimizing the chance of picking scattered. So what does Compton scattering do? We talked about this briefly. Compton scattering essentially causes blurring, right. So I am looking at the straight line path, but then something Compton scattered is coming and getting hit at the detector. So my model, I can only say, because I do not know. So I am just sitting here, the detector is just receiving it. So we will only pretend our model is, oh, it is coming from straight line. So whatever came from here, we will assume, we can only assume it came from the straight line. So essentially what happens is, your blurring, your resolving capability goes down. So there is a blurring because of Compton scattering. So we talked about this before. So it's an undesirable aspect and we need to reduce it. How do we reduce it? Maybe we don't want to collect that in the detector. Before it hits the detector, we want to make sure that if there is a possibility, we can make a kind of a filter again, right? I would say some ways where it's like a gating mechanism. I will only allow guys who are coming along the straight line. Whoever is coming on the sides, I will not allow, right? So that's what these grids or air gaps or scintillation slits, their job is before we hit the detector, how do we ensure we get rid of scattering, or at least the photons that are coming through scatter, minimize the photons that are coming through scattering. So how to reduce the scatter, that is the goal in this part. Okay, so there are 3 ways to do it. We'll quickly go through each one of them, but in some sense just by the problem proposition, right, and the name that is there, we can start to guess, right. So grid, right, so this is what we are talking about. You have your X-ray, the X-ray is sending at some angle, right, diverging, and before it hits the patient or the object, right, we cannot, we are not, that part is fine, that part is done. But after it comes out of the patient, so there is an angle, when it goes hits the patient, there is a diverging angle, that is fine, same line of sight is what we are going to use. But the problem arises because after it passes through the patient, the object, 3D object, you are going to have scattering. So that means there is going to be angle. So the detector is now going to not only have the line that you have from the source, but because of the Compton scattering, you can have different angles that are coming in. So now the objective is, how do I allow only the signal that was coming, or the photons that are coming along the line of sight, and minimize the ones that are coming at different angles. So how do we so clearly it has gone through the patient. Now we are talking about coming outside the patient. It's Compton scattered and coming out. If it is Compton scattered and absorbed by the patient, we cannot do much, right. Our interest now is assume we have sufficient signal that is coming out, which we want to detect, so that we can form an image. So in such a scenario, something is coming out. How do we minimize that in the detector, right, minimize the Compton scattering in the detector, so that the image quality is not compromised, right. So there is a grid arrangement. So in some sense you can think about it as, that means is there a possibility where here, for example, you have a grid of lead strips. What will lead do? If the X-ray photon hits the lead, it has more attenuation, right. So it will get absorbed. If the length, the thickness of your lead is going to determine how much is going to come out. But clearly outside the body, when it comes outside the body, all the X-ray photons you want to capture in the detector. But then I want to absorb, I don't want the detector to even receive Compton scattered photon. So what can I do? I can have lead such strategically organized. What is strategy here? Oh, it is now a linear, it is organized in a linear grid fashion. Not only that, you probably can appreciate that it is not like parallel lines. So it is kind of having a focus, there is a tilt to the, there is a tilt that you can see. So it is focused, so that this line of sight, right, is kind of what they call as focused grid. So because this is coming from diverging, there is a tilt, so that it is all focused, all the slits are focused. So what will happen? You have lead, and in between the lead you have a transparent. So it can, if it is not hitting this lead, it will go through. So in some sense, if it is coming through the line, if it is only the photons that are coming through the straight line, right, will pass through without hitting the lead. If it is coming at a different angle, it is going to hit the lead and therefore get absorbed by the lead. Alright, very nice way of thinking about it. So what are the factors? How can we, okay, it is strategically arranged, but how can we engineer it? So intuitively thinking, If I don't have any grid, what is going to happen? Every angle it is going to come and hit, right? So it is going, detector is going to catch at every angle. So when you look at this, the other extreme is I have lead, right? I have lead that are next to each other, right? So there are two factors. I can have lead next to each other, which is controlled by the width, which we call B, and what is the thickness of or the height of your lead, height of your lead. Both of this is going to affect what is going through the, so the width is going to dictate the distance between your lead is going to dictate, because that is the transparent, the distance between them is the transparent. So that is where you are going to go through, right? So in some sense your B and height have a role, right? So if I have intuitively thinking what factor, what what relationship between H and B is helpful for you, right? So we could kind of think about this as your H, right, effectiveness. So effectiveness of a scatter, how can we measure it? What is the effectiveness? I want only the straight line to come through. I want to obstruct whichever is coming at an angle. So I want the lead to catch the ones coming at an angle, the Compton scattered one. So how can I do, talk about effectiveness? Oh, I can talk about effectiveness by intuitively thinking about what is a favorable condition. So I have one is H, the other is B. If I have very right, if if this is the direction, this is my source, this is my detector, and I have this grid here. So you can think that if the height of the grid is more, then there is a good chance that the more angles will be hitting the lead, it cannot go through. If the height is less, different angles can go in. So having a height, tall or short, which is favorable? Okay, then what about your B, right? B is the distance between the leads. Again, what is favorable? Well, if I have a height, right, this is length is more, then in some sense that is going to have a shadow, right? Right, it can protect, it's all about the angles. So it's more about the H by B, both of them, right? So grid ratio H by B. So I want to make sure that this ratio I can manipulate to our advantage to talk about effectiveness. So typically you have about 6:1, you normalize it for B and report. So you have about 6:1 or 16:1 in conventional radiography. So this is a trade off, right? So but this is the range over which this H by B is used. So this is essentially to reduce the scattering. So your tolerance, how much Compton scattering you want to reduce. This H by B, that the angle, right, that is going to help dictate how much you can arrest. So if you have a very large H, right, so the H by B ratio is large, that means you are going to be very strict. Or I can be tolerant, the H by B ratio can be small, which means I can allow for little more angles coming in, right. So you are essentially controlling how much of Compton scattering you want to arrest. Okay, this is something, if you really think about it, when we talked about, we did one simple calculation, right. Recall when we talked about number of photons that are lost, H mu and H mu dash, the energy and number of photons and the angle at which it can hit and still be considered straight line, right. Some 26.4 degrees, if it was hit, you still consider it as straight line path. Go recall that example that we did. when we talked about Compton scattering. Okay. So, in some sense your grid ratio tries to adjust for that angle. So, you can be very tolerant or less tolerant of the Compton scattering depending on this ratio. Clear? So, this is fine. What are the other parameters? Okay, this ratio is important, but this is normalized, right? One is normalized to width. So, to get a feel for this, what is this B? It is the distance between the two lines. Instead of saying like that, a common way of describing this specification is number of lines per centimeter, right? So, you can have say somewhere like 60 lines per centimeter to 80 lines per centimeter. Your instead of reporting it as B, you can report at number of lines per centimeter. So, roughly you have 60 to 80 lines per centimeter in a typical system, depending on the application. Either it's for mammography or is it for chest X-ray. Depending on the application, that can vary in that region. So, you have the ratio and the distance. Both of these are manipulated based on the application and level of noise that is tolerated, or signal to noise ratio, contrast to noise ratio that the physician is okay with to make a reliable diagnosis. You see, it's always a trade-off. That is the whole point. Okay. Okay. So, this is with respect to reducing the scattering. Yeah, can be as low as 2:1 for mammography. Okay. Fine. So, that is with respect to your grids. Now, the question is, well, you are talking only about reducing the scattering, right? We talked about just reducing the scattering, but what am I interested? Oh, I need to have not just reduce the noise, right, scattering. I need to have increased the signal to noise ratio or contrast to noise ratio. But what happens when I use the grid? Whatever is coming at the angle I have reduced. But what happens when the lead, so when the signal, like the photon comes and hits the lead, there is a grid of leads, right, or attenuating material. What happens when the photon is actually hitting that? Well, if it is hitting that, that is also lost. So, in some sense you are getting the signal only through the transparent window that is adjacent to the leads, right, that is sandwiched between the gap between the leads. Not only you are hitting the height of the lead controls which angle it is hitting, that is absorbed, but depending on the height, when whatever is coming and hitting the lead itself, that is also lost. Your signal is also lost wherever the grid is actually physically where the leads are placed. So, in some sense I have reduced my noise, but I have also reduced my signal. What is of interest? Increasing signal to noise ratio. One way of doing that is reducing the noise for the same signal. But if signal is also reducing, is it prudent? Clearly not. So, how can we increase the signal, right, for the given reduction in Compton scattering or the noise? The only way is increase the number of photons. If you increase the number of photons for the same schematic, right, then whatever is Compton scattered will reduce because of the grid. Whatever the signal is lost due to the grid placement itself, you get more photons that are coming through because you have increased the absolute number of photons that are coming through. That means your exposure is increased. So, there is always a trade-off. Your exposure is increased, but you get better signal to noise ratio because the grids have reduced the scattering. So, how do we talk about this scenario? So, for example, I want to increase the signal to noise ratio. Should I use the grid or not? Am I going to get better rewards for increasing that exposure because the quality is increasing, or essentially I end up with the similar ratio of your signal to noise ratio, that there is no point in increasing the dose when your signal to noise ratio is about the same, right? What do we do? So, we have what is called as grid conversion factor. What is the grid conversion factor? It is the MAS. What is MAS? Oh, current into time, MA, milliamperes, tube current into S, your time. Oh, that had to do with our exposure. So, exposure with grid to exposure without grid. What does this convey? Oh, if I don't have grid, right, if I don't have grid, what is the scenario? I have some exposure without grid. So, there is some n number of photons that are coming. But then the scattering is also high. If I have grid, with grid your scattering is low. So, what do you think this ratio is going to be? The moment I use grid, right, the moment I use grid, my noise is going down, but my signal is also going down. Whereas without grid, I have both. Signal is also there, noise is also there. So, now what does this GCF do? GCF allows us to capture this sentiment. How much of the signal to noise ratio you are gaining because of having the grid, right? Or rather, if I don't have the grid and if I have the grid, what we know already is if you have the grid, you may want to increase the signal, otherwise you are losing the signal also. So, this grid conversion factor tells you how much you should increase the exposure if you have the grid compared to when you don't have the grid, to compensate for the loss in the signal and of course reduced in the noise. Okay. So, typically a grid conversion factor is about 3 to 8. So, grid conversion factor into exposure without grid is equal to the exposure with grid. So, if you look at this number here, that means it is saying if I use grid, the exposure with grid is several times, right, because 3 to 8, several times the exposure without grid. Clear? So, how much is it? This is the factor. So, you have to increase the exposure. So, that is a trade off. Depending on the application, the doctor decides whether it is favorable, it is worth increasing the grid conversion, increasing the signal to noise ratio by increasing the exposure or not. So, if I increase this, if I introduce this grid, then my quality goes down. So, I have to increase my exposure. So, this is where they make their domain knowledge expertise. So, think about when you maximize the signal, when you minimize the signal. Your noise is Compton scattering. When all can it happen? Well, so you are introducing this grid to reduce the Compton scattering. When all can it happen? Oh, I can have it goes in, I have Compton scattering. So, if the thickness is more, right, if the thickness is more, then there is a chance of more Compton scattering coming out at angles that are going to cause problems. So, a rule of thumb that they have figured out is if it is less than 10 centimeters thickness that we are talking about. So, if you go for your arm imaging, you break a bone or suspect that you break a bone, maybe it's very it's not that thick, right? The depth you can place it so that it's not much thicker, 2, 3, 4 centimeters, something like that. You don't gain much. At least they have found that it is not worth having a grid conversion factor and having increasing the exposure. It's not worth, because the Compton scattering itself is going to be less, because the thickness of the material is less. So, as a rule of thumb, if it's greater than 10 centimeters, then they want to consider introducing the grid. That's when they believe that the benefit of introducing a grid outweighs the cost, that extra exposure that you need to do. The other way is, that is one rule of thumb. The other is regarding the energy. When do you have Compton scattering? At all energy levels. And if you look at the signal, right, there was a hill curve. So, if you are going to operate at a lower energy level, then you are not going to benefit much, because even if you increase the exposure, the inherent contrast, right, the interactions is going to be limited, and so you are not really going to benefit much. So, Another rule of thumb is whenever you want to have the grid, whenever they have greater than about 60 kilo electron peak, when you are operating the X-ray tube with greater than 60 kilo electron volt peak, that time you want to introduce this grid. So these kind of domain specific, application specific, experience based empirical rule of thumbs have been evolved, whether to use the grid or not, because of this grid conversion factor. Either you don't want to increase the exposure unnecessarily if you are not going to gain much in the signal to noise ratio, or the reduction in the noise due to the introduction of the grid. Okay. So another problem is, apart from the grid conversion, because you have to increase the exposure, the other problem with the grids is you are going to have shadows, right? So I mean it is difficult, because when a camera is in front of me and I cannot show the shadow because the camera will obstruct it. But the idea is, if this is the grid, right? If I don't have, if I have the light coming in, there is a shadow behind, right? If I move the grid, there is an opening and the light can come. So you can clearly see a shadow of my 4 fingers, or this is the grid, for example, right? LED grid. So clearly, if on one side you have photons come, the other side you have a shadow of the grid. Okay, so that is not the shadow because of the material having a grid light structure. That is not because of the material having a grid light structure. It is because of the grids that are there. So it's an artifact. So how do you reduce that? You can move the grid during exposure, so that you can blur it uniformly. So there every location, right, in between the grid. So when you move, the location of the grid is also moving. So you can smear it throughout the background. In some cases, willfully you are smearing it, blurring it, so that it is all homogeneous. Therefore, whatever differential you have is only due to the difference in the tissue. Okay, so you can do it like that. Last but not the least, air gaps. Air gaps is again not really a big instrumentation aspect. It is just using this knowledge that you have the line from the source to the detector through the object. So there is an angle at which it is coming. The Compton scattering happens, the origin of Compton scattering is inside the object. So the distance between the object where the Compton scattering originates and the detector, that angle is going to be different from the angle of your source to the detector. So in some sense, if the detector is moved away from the object, then we could separate out these two angles. Okay, so in some sense it is not really an instrumentation. The idea is to exploit this knowledge that if you have a gap between the detector and the object, basically air gap, if you do that, you naturally reduce the Compton scattering. Of course, this is not so great, because you will see that it also affects the signal and the contrast and the when we talk about imaging, right, the effect due to this distance between your object and the detector in terms of magnification will all come into picture. So it's okay, it's a slight maneuvering, but it's not that great. Again, scanning slits. We talk about slits when we talked about slits in the context of outside X-ray tube, when we wanted to do the field of view, right? So we said slits is one thing. So you can have actually slits here also. In some sense, what do we want? We have grid. Now we are talking about the problems due to grid and how it arrested the Compton scattering. So why cannot we have slits, right, in front of the object and back of the object? So this is slit 1, right? Slits, you have openings. I have another slit, openings. So I can have one in front of the object, one in back of the object, right, and they both are aligned nicely. Then what is going to happen? Instead of sending the X-rays in the grid, what happens? It goes through the patient, right, and the grid is behind the patient. So So the signal that came through the patient after the interaction, when it is hitting the grid, that is lost. So you have dosed the patient, but you are not exploiting that signal. Instead, what we can do is, you can have the slit also at the beginning. That way you don't even dose the patient where the grid is, right? So you align these two perfectly. That way only through the transparent in between the slit locations the signal is going through. Every other angle, even here, it is arrested, and therefore whatever comes out of Compton scattering you can manipulate here and it can get arrested. So in some sense you have reduced, instead of sending the signal through the body and getting hit by the slits here or grids here, I can only send in at locations where there is no slit, where there is no grid, right? So I can have a slit that is perfectly aligned. So now what will happen? Oh, now we get best of both, but the only problem is the signal is lost, you don't get signal. So you have to increase the exposure, right? And also here in this sense you are not scanning, you are not going through certain locations wherever the slit is not allowing it. So what we can do is have these two slits and move these slits, right? So what we call as scanning through the slits. This way you can reduce the scattering, you can increase the signal as well. So it's very effective in reducing the scatter. But the only challenge is instrumentation is little bulkier, you have to now synchronously move these two, and exposure is also increased because you are getting more shots at it while it is moving different locations. Of course time is also little more because now you are scanning few locations so that you don't have these shadow locations. That is the downside, but then you get good signal to noise ratio. So this is again something that is used in higher end systems. I think this is a good place to stop before we hit the detector side of it. That will be covered in the next lecture. Thank you.